All right, so last time we talked about this idea of a tensor decomposition being a generalization, right, of an SVD, right? So this idea of this having sort of the dominant correlated structure, but now instead of doing it with data matrices, you now do it with data hypercubes, right? So the idea being, in a pictorial way, if I have a data matrix, we know that we can decompose this with an SVD, and we could represent this as something like this, as a sum of U1, U2, and this here would be sigma 1, V1, sigma 2, V2. This is that's V2, yeah, plus so forth. So this is the idea behind the SVD right there, right? You take your data matrix and you decompose it into different rank 1, rank 2, rank 3 as you go down. And of course, you can rank truncate it. So this is a very compact way because this is a single vector that spans the dominant correlative structure of the data in the column space. That's a second, or it's orthogonal to the first, and it's in the second direction for the most correlated activity. And the V's tell you something about the row space spanning. How does this mode span that row space of that matrix? Okay, so we've spent a long time talking about this. We've done some homeworks on it. Not only that, you've also said, well, if this is a massive matrix, last time we were talking about randomized algorithms, I can produce these different structures using random projections of that data matrix to produce this. So that's the concept behind taking a data matrix and doing a decomposition. And SVD is kind of like your go-to method. SVD is like the one decomposition in life that if you have that one, you're fine. It's the go-to, okay? What we want to now do is switch it to think about how do I generalize this concept to higher dimensions, okay? So let's go ahead and start talking about that. So if you generalize this to higher dimension, well, one more dimension up would take the data and you might put it into a data cube, okay? So now here, we would specify every component in this matrix as an Aij, so row, column. Here, there is no row column. There's just different dimensions. So you'd say Aij, K. And by the way, this is trivial to do in MATLAB. It is really easy to make data cubes, hypercubes. You can make 4-dimensional, 5-dimensional. And this is very common, by the way. Right? So think about if we were to take people and take representative data of every single person, we are in fact an n-dimensional kind of interesting objects, right? We could say, hey, this person here's their height, here's their weight, here's their eye color, here is their inseam, their chest measurement, their nose size, how many cavities they have, gene expression of some sort. Do you have, this or that or the other? So if you think about representing you are an n-dimensional object in some data matrix. Now, what normally we did and what we talked about last time is you say, even though this data is n-dimensional, often what we do is we take that data and we do the vectorization. Right? So that's normally what we do is we say, well, vectorize this. So take this, vectorize it, and then you can use standard SVD. But if we don't want to vectorize it and we really want to keep these different dimensions of ourselves separate or different dimensions of the data separate. So for instance, even if I was measuring things outside, I could measure pressure and temperature and time of day. These are all different characteristics at different spatial temporal locations. And I don't want to flatten temperature with pressure with oxygen concentration. Like these are just different quantities, and I want to keep them in some sense in different dimensions. Okay, so I would like to still do a decomposition without doing the vectorization process. So remember, the way you would do this is it's exactly like this picture here. The tensor decomposition is then, how do I produce the equivalent of this is now this. So now I am spanning all 3 dimensions of this cube. Now, if you go to 4 dimensions, then there's 4 of these. So every dimension has sort of a spanning vector. Okay, and you would just add them together. And here I've put the sigma 1 with each of these, but you can imagine this is some lambda 1 plus some lambda 2 and so forth. So this is oftentimes called a factor analysis. Here are the factors of your data separated. So one way to think about an n-way decomposition or an array decomposition looks like this, or a tensor decomposition of this, is it's a factor analysis. I look at the different factors, which are different directions of this data, and I look at the dominant factors in this decomposition. These are equivalent, okay? Except for some of the questions asked last time were, why would we do this vectorization? Why not just do this? This here in matrix form, we have developed decades of fast, stable algorithms. So we're very mature computationally here, and we're less so here, okay? So this is something that just, so even though philosophically they look the same, there's just orders of magnitude difference in terms of the amount of time spent writing algorithms here versus writing algorithms here. Okay, so this is what we're going to do is we're going to actually play around with this today and actually do a little example and show how it works and show how the decomposition does these things. So that's the idea. So let's go ahead and I'm going to give you an example of what we're going to do. So I'm going to take a data set and we're going to do this kind of decomposition with it. Okay. So here's what we're going to do. I'm going to give you a function. And I guess I could have kept my cube. Here's my cube. Here's how I'm going to arrange my data. The data I'm going to put in here is that in this direction is x, y, and this will be t. So I'm going to make a function that's like basically a spatial function in x and y directions. It's going to be changing in time. So this might be something like a video, right? A video is an x direction, a y direction, and then it's changing in time. Okay? So that could be, each one of these is a slice of a video. But here's my simple video. I'm going to put in 2 modes. In other words, 2 different fundamental features, or you want to call them, it's going to be a rank 2 decomposition. I'm going to put 2 objects in there. And what the question is, I'm just going to mix it together and then ask the question, when I do this decomposition, can I pull back out the two features I have? So here's the first feature. First function is, it's a function of x, y, and t. I'm going to put a Gaussian, e to the minus x squared plus y squared. So that's the spatial structure I want. It's a Gaussian. And what I want this Gaussian to do in time is I'm going to just do something simple. I'm going to make it oscillate. So cosine 2t. Okay, so this is just a little bump oscillating up and down. Okay, centered in the domain. I'm going to put a second object in there, f2. And what this is going to be is a different little bump of sorts, but it's going to be, here's what it's going to look like: hyperbolic secant, hyperbolic tangent. So what such tangent looks like is something like this. And that's in the x direction. And I'll multiply that by a Gaussian in the y direction. Okay, so it's this structure in x, and then in y, it's a Gaussian. So in this direction, it's a Gaussian. That's what that's going to look like. And what I'm going to make this do in time is oscillate with sine t, which is a different frequency, half the frequency. Okay? So these are my two functions. And what I'm going to do is say, well, my data matrix F is going to be a mixture of F1 plus F2. So I'm just going to add these two together, and that's going to be my data matrix F. That's what this is going to be. So I'm going to have XY slices of time. And then the question is, I've put two objects in there, two features, and I'm going to let them evolve in time. And so what I'd really like to do for this experiment is ask the question, if I just give you F, can you give me back its constitutive parts? In other words, can you give me back F1 and F2 and give me those features, those factors that made up this data? Okay, so that's essentially what this does in 2 dimensions. And this is what I'm going to do in 3 dimensions. So I want to be able to pull out the 3 vectors. Remember, what I'm going to get out of this is these structures, right? So the modes are going to be, here's what it looks like in Y, here's what it looks like in X, here's what it looks like in T. And the question is, there's 2 modes in here. I'm going to get 2 sets of these, and I want to know what those look like and say, if I put that data in, can I bring this back out? Now, this is a very simple example, but it highlights how to do this tensor decomposition of data, which is equivalent to doing the SVD, but now you're working in higher dimensions. And now you're not doing this vectorization. You're just going to be able to do this directly straight here. Okay? So that's what we're going to do. All right? So I'm going to walk over here. I'm going to sit down as we program. Okay, let's take a little hike. I feel like Mr. Rogers. Well, come over here. Let's say hi to the fish. Oh, hi, fish. Oh, you see my fish there? Oh, he wants to do this fish knows more MATLAB than probably any other fish in the world. So anyway, there you go. My fish will be a YouTube star now. All right. I guess I got to share screen now and stop messing around here. All right. So share screen. Okay. The whole desktop. Okay. You guys all ready to program? Hopefully so. Here we are. I'm going to go ahead and start here. So I've already pre-programmed some of this so that we can just kind of quickly get down to do some analysis and visualization. So what I'm going to do is start here. Here is my basic domains. So X is going to go from -5 to 5 with 0.1 points. Y is going to go from -6 to 6 with 0.1 points. So those are my XY domains. I'm just making them different. So it's not a data cube, it's a data rectangle. And T is going to go from 0 to 10 pi in steps of 0.1. Okay? So those are my 3 spatial directions. And then I can use the mesh grid command to make these capital X, capital Y, capital T, which are essentially vectors. Now they have the 3D structure built into them. Okay, that's what mesh grid allows you to do. It allows you to construct these vectors in such a way that now you bring in all that information and for it to understand that there's 3 dimensions to go. Okay. Now the matrix A is here, but what I'm going to do is start building the pieces of it. Let's look at what they are, and so you can see what we're actually trying to get after here. So F1 is going to be this guy right here. Look what it is. It's a Gaussian, just like I drew up on the board. It's -x squared. Oh, and plus 0.5 y squared. So it's actually not a Gaussian, it's an elliptical shaped Gaussian times cosine 2t. F2 is this other one here. Okay, there it is. It's this one here. So it's sech tanh times, now it's a Gaussian in y times sine t. What I would like to do with this is actually plot each one of these individually. So let's do this for j equals 1 to the length t end. So what we're going to do is make a little movie, and you're going to see what this looks like. So your movie is going to just, what we're going to do is just simply plot frames of this. So we're going to do, for instance, p color. And what we're going to plot here is x versus y versus f1, but each frame of f1. So we're going to do f1 go to the jth frame. So notice f1 is a 3D cube of data, okay? In fact, what we could do is just when I do x1 and x2, let's go see what size it is. So let's go here, run this. And when I do here, I'm going to come over here and say size f1. So f1 is a data cube, 121 by 101 by 315. So it's got 121 points, right? And I think that was the y direction. I've got 101 points in the x, and then I have here 315 points in time. So that's what I have right there. So I have a data cube. And by the way, how easy is it to make, for if I want to make something like rand and 20 by 20 by 20 by 20 by 20 by 20. Oh, I should not have it. Sorry, I should have put a colon, semicolon on that. It's too big. Okay, so, all right, let's do this again, but just do that. So now it's going to make this, and I do size B, right? Size B. So I just made a cube, a hypercube, which has 6 dimensions to it. So you see how easy this is? MATLAB doesn't care that you're working with matrices. You can do anything you want, right? You can make this a hypercube of higher dimensions. But once you commit to this, right, this hypercube of 6 dimensions, if you want to do like something like a decomposition to look for low rank features, you have 2 options. Option 1, you have to vectorize this into a one giant vector. Or, so you collapse all those different dimensions, which can be quite different, out into one vector. Or the other option that you have available to you is to do a tensorial decomposition of this thing and keep yourself working in a 6-dimensional space, okay? So an n-way array. So those are the options that you have available to you in working with this data. All right, but I'm just trying to show you how easy it is to do this. So now what I want to do is take this here. I have these data cubes, and let's go ahead and make a movie here and show what this looks like. P color, sorry, I want to do a shading interp, and then draw now. Okay, so what this is going to do is going to go through this loop to the length of the t. So it's 315 time snapshots. And what you're going to look at is x versus y versus f1. And we're going to make color map hot. And it'll draw that. So let's do it. It's going to make a movie. Oops. What does it say? Matrix dimensions must agree. Let's just check it out. Size f1, size x, y, oop, size y. Okay, so x and y are all there, and oh, you know what I'm going to do is do this versus, sorry, x versus y. There we go. It has to be little x versus little y to keep this consistent. Okay, so this should work, I think. All right, still complaining. Oh. Oh, no. There we go. All right, okay, that. Oh, that's not getting anybody sick, but this is just changing a color map because this thing is going up and down. So let's actually put a, anyway, that was probably not the best drawing of this. Let's do a surf L. we'll do color map gray. Okay, so now what we'll do, and also we probably want to fix the axes so that you can view this better. So we'll do axis. It'll go from -5 to 5, -6 to 6, and the heights, yep, and then -1 to 1 in those directions. Okay. So I'm just trying to show you what this thing looks like in a kind of cool little movie. All right. Oop. So let me just check here. What my problem? X min, Y max. There it goes. Oh, Z min, Z max. I should have it all there. All right. I'm not sure what the problem is. Let's just do this. All right. There we go. Let's just run this thing. There we go. It's going up and down like this. And I could even pause it to make it go slower, but you get the point. So this is one of the features. And how did I construct it? In the X direction, it's a Gaussian. In the Y direction, it's Gaussian. And in time, it's a cosine 2t. Right? So with those three vectors in these three different directions, I constructed this object, which is part of what F1 is. F2, let's do that. If I do F2, something similar, it's just like this. It's like so it's still kind of a localized structure. It's a little bit different than the first one. This is oscillating at sine t, right? So it has the omega there is 1, where the other one is cosine 2t, so the omega there was 2 with the frequency. Okay? So I wanted to show you these structures, which again were made up of one vectors in each of the different directions. Okay. So let's go ahead and kill those off. We don't want to see them anymore. I have the data, and remember that F is now F1 plus F2. So the idea here is that in fact, let's call this the matrix A or the tensor A, right? This is a tensor now. And so what I want to do with this is I've given you a tensor, F1 plus F2, which are these objects interacting together. Now, if you're given this data, and you didn't know there's an F1, F2, the question is, could you from the data matrix S, A, or the matrix or the tensor A, get back for me the constitutive parts that made it up? That's the entire idea of the SVD, right? Is to go back and look at the low rank underlying structures that produce that data. That's what we're going to do here as well. Okay, but now it's in higher dimensions. All right. So, sorry, I'm looking for one thing quick. Okay, so now let's go ahead and do a tensor decomposition of this thing. And because one of the options, of course, is I could flatten it. And by the way, maybe I should show you how to flatten this real quick. I can do the following. I can take this matrix A, and if I want to flatten it, let's make a new matrix AF, which is a flattened version of this. And what you can do is you can, in fact, flatten. What you really want to do with this thing, right, is you want to take F1 and F2, the X and the Y, and flatten it into a vector. So let's go back to the loop for J equals 1 to length T. And there's other ways to do this, but I'll just show you how to do this here. You can say, what I want to do is I want to go grab, for instance, A, and go grab the jth component of it. Okay? So I'm going to go grab, remember it's X, Y, and Z, or X, Y, and time. I'm going to go grab the tth column of time. And what I'm going to do with this is I'm going to take this thing and reshape this into a vector, which is, let's actually do the following here. Nx is the number of x points. So this is the length
of x, and y will be the length of y. And when I reshape this, I want to reshape it to size nx times ny by 1. Okay, so I'm going to take that, reshape it. So now this is a long vector. And what I want to do with this thing is make a new matrix, call it AF, whose jth column okay, so I'm going to go and grab and make this column J, all rows will be equal to this thing I just reshaped. Okay, oops, sorry, I want the jth column, right? I want this. So I reshaped this thing into a column vector, and I'm going to make AF be, there's the column. So I just took this data, I reshaped it, put it in as a column, take the next time stamp, shape it into a vector, put it in there, and AF now is a big matrix where each column is this XY structure reshaped, and then I've stacked up the columns. So I've made a matrix where I could just apply the SVD on this. So if I run this thing, let's go ask, what's the size of AF? So I reshaped it, and this thing is now 122221 by 315. So this thing here tells you what I've done is I've reshaped the X and Y coordinates to be one giant vector, okay? And then now you could do all kinds of things because now it's a matrix. So you could do SVD, you could do whatever you wanted. And if you want to get back to what you had, you would take this thing and you would grab each column and reshape it back into the inverse reshape of this is to take the A of F. Let me go ahead and show you how to reshape it back for J equals 1 to length T end. So this is, call this the vectorization process. And this is make it back to a tensor. Okay. You go through each row and you take the A of F and you go grab the jth column, and what would you do? You'd reshape it. And how do you want to reshape it? Back into an nx by ny. And let's call this a tensor, which is this. And that's actually, so this will get you this reshaped version, which is nx by ny and j, something like that. Okay, so there you go. You go grab the jth column. It will go fill in the rows, columns here, and j. So now you have A of t, which is back to what you had before. So you can reshape in, reshape back. So you have to do this if you're going to decide to work with the matrix formulation. Okay, so if you want to stay with matrices, that's fine. You could do the SVD in this matrix, but you have to always do the reshape back out. And by the way, if you have 6 dimensions, you just reshape them all into a vector as well. The reshape command is fantastic for doing this stuff. And there's a similar command in Python for doing it as well. Okay, so that's what we have for if you're going to stay with vectors. But now what we want to do is say, okay, but now I want to work with tensors. By the way, I don't know if anybody saw, I'm calling this code tense.m. I'm not tense, but I thought it was a good one. Tense.m, we're going to run this in a minute here, and we're going to take this data, and now we're going to just show you how to do an n-way array. So let's kill that. And we'll kill this plotting program as well. So what I've done here is, if you go to MathWorks Central, so that's MATLAB sort of Uber site where you can go download codes and so forth. There was a code written by Erasmus Bro. And Erasmus Bros does an n-array tensor decomposition. And in fact, I have it here. So this is the package. You can download it. It's called n-way n-way array. So you just look up n-way array in MATLAB and MathWorks, and you'll find it there. You'll have to log in, sign in, and you can get this package. And what he did is he wrote a package that would do a parallel factorization algorithm, which is n-dimensional, okay? So what it wants to do is it says you give it a data cube, a hypercube of data, and what it will do is it will look for the dominant factors in each direction. Another way to say factor is principal component, or that's the generalization of that concept. Is a factor analysis is you can have multi-dimensional factor analysis. In other words, you have not just u and v, but now you have u in this direction and u in this direction and u in that direction. You have a u vector that is in each of the different dimensions of your data. Okay, so that's what the factor analysis would do. So here's the simple lines of code that will do it for you right here. There's more to this package. I'm just going to give you the very, very basic structure of the package. Model. So I'm defining model as parallel factor. So this is a .m file that's in this package. You give it the data matrix you want and the rank you want. Okay? Give me a model, which is a parallel factor model of the matrix, say, into two components, right? So obviously what I did is I put in two components. So I know what I should be looking for in terms of the rank. But this 2 here is really your rank. Okay? So generically, you're going to have, you're not going to have such nice data. So you might look at a 10 rank model, a 5 rank model. Just like you did in SVD, you have to decide where you rank truncate. Also, you have to determine how many factors you want. What that's like the equivalent of this thing. So this creates this object called a model. It's a parallel factorization of this matrix A, of this tensor A, to 2 dominant components. And then you can change this model using this fact-to-let command. And what this is going to produce for you is vectors of each of the principal directions that you get out of your factor model. Now remember, I have a data cube, so I'm expecting for each of the low rank projections, I'm expecting 3 vectors. 1 for each of the different that spans each of the different directions of this data cube. Okay, so A1, A2, and A3. Those are the different directions I have in this cube. Okay, if I had a 10-dimensional cube of data, I would expect A1, A2 all the way through A of 10. These are the different directions, and this is basically going to go act on this model to produce for me these different directions. Okay, and for each one of these directions, I get 2 vectors because I've said, give me a 2 component, give me a rank 2 system. So in the first direction, give me 2 vectors. That's like U1, U2. In the second direction, give me 2 vectors. That's equivalent to like, give me V1, V2. In the third direction, give me 2 vectors. That you get the idea. So that's it. It's as easy as that. Tensor decomposition. And then we're going to plot some of this. So what I'm plotting here is 3 subplots. I'm going to plot X versus A2, X versus Y versus A1, and T versus A3. So what this is going to show, basically plot for me. It's going to basically plot these different factors as a function of the different directions they're in, as a function of X, Y, and T. And let's go see what they look like. So let's go ahead and run this. And here we go. We're done. That was pretty fast, right? But it's not that big of a tensor. So there we go. So now what are you looking at? This is the these are the factors that pulled out for us in the 3 different in the 3 different directions of X, Y, and sorry, actually I had it backwards. Y, X, and T. In the Y direction, I have two Gaussians. But that's exactly what I put in. Notice what I put in here is here are the x directions. So first of all, in the x direction for the first function, just a Gaussian. And for the second function, sorry, they were in the y direction. So it's a Gaussian in the y direction, e to the minus 0.5 y squared. And then here, this one is e to the minus 0.2 y squared. So one's minus 0.5 y squared, the other one's minus 2.2 y squared. And that's why you see two Gaussians here. By the way, notice something. When you do an SVD, these are unique up to a sign. So I could easily multiply any one of these by -1. In other words, I could just flip this thing upside down, this orange one up, and it would be equivalent. Okay? It's just like eigenvectors. You can have them up, you know, which side they actually get flipped on is sort of flip a coin. It doesn't matter. It's just you determine these two within a sign change. So good. In the y directions, I have Gaussians. And notice it goes from -6 to 6. Here is the x direction. And what kind of functions did I have in the x direction? In the x direction, I had Gaussian. There it is, e to the minus x squared. And in the x direction, I had sec-tanh, which is exactly what this thing looks like, this orange one. So you see, I reproduced the factors that I actually put in. So again, this is a very simple example, but it illustrates for you that like you get back what you're supposed to, right? You totally nail it. This factor analysis didn't know about your functions. It says, when I take this data and I look at it, here are the dominant structures that compose it. And same thing here with the time dynamics. One is cosine t, one is sine, what was it? In time, it's sine t, right there for the F2, and it's cosine 2t, so it's twice as fast for the first one. And notice the blue, which is the first one, cosine 2t, it's twice as fast as that red one, which is sine t. So in other words, what I actually put in was these reds multiplied together. This guy times this guy. And then I also put in the blue, which is this guy times this guy times this guy, those blues together. And it got it for me perfectly. So this is just a really simple example of how this factor analysis can work in higher dimensions with this n-array decomposition. And again, here, I didn't separate the kind of data that you were putting in, right? This is all sort of, in some sense, simple data. It's not distinct different types of data. And so it works great. And you can see that I easily recover what I'm supposed to. So it's a sanity check more than anything else, that in fact, you can take this tensor decomposition tool and just produce these different factors in different directions. Now, where it's especially important is when you do this with data which is different types. So in other words, again, suppose I was measuring different features of people, right? Where we say, oh, these different dimensions are things like, you know, eye color, height, weight, hair color, waist size, I don't know, whatever. These are things that you don't necessarily want to just vectorize and say these are all common things. You want to actually maybe keep these kind of very different type of quantities separate for yourself. And this allows you to do that very easily. You do not have to mix your data. You keep them separate, and then you look for low rank structure within these array structures. And again, I think that's really important. It's a generalization of linear algebra, right? Linear algebra, we just said matrix. That's it, 2 dimensions. And what these arrays are telling you is like, there is no reason to constrain yourself to 2 dimensions. In fact, you can go to n dimensions and things work just fine, except for that we don't have quite as sophisticated algorithms for the n-dimensional arrays, but it's just a matter of time before it changes. So it will change in time. All right, so there we go. That's what we learned today. And let's see if my fish will say goodbye to you. Oh, you guys scared him. Maybe he'll come back. Anyway, let's finish the lecture there. And I will take questions.